Let's take a little bit of time here today and talk about momentum and impulse, our first unit of the year. We defined momentum on the very first day in kind of an everyday language is how hard it is to stop something. But in the end, we know that that comes from the real definition of momentum, which is the product of an object's mass and velocity. And really, that boils down to an equation. P is equal to m times v. The units for momentum, of course, we can get the units from here. You can get the units from any equation, right? You're ever wondering what the units for a variable is? You can get the units from any equation. For this one, we'd say, because it's mass times velocity, we'd say it's kilograms times meters per second. There is another set of units that we can use for momentum as well that we learned later on when we talked about impulse. Does anybody happen to remember right now what that other set of units is besides kilograms meters per second? Not newtons per second, but you're close. Yep. Good. It's newtons times seconds. You don't need to worry about converting back and forth between those two variables or between those two units, because in the end, 1 kilogram meter per second is exactly the same thing as 1 newton seconds. We just usually use kilograms meters per second when we talked about momentum and newton seconds when we talked about impulse, but really they're the same thing. Listen, these are pretty straightforward, right? You got to be able to take the velocity, you got to be able to take the mass in the right units, kilograms and meters per second, and multiply them together to get momentum. You also have to be able to rearrange them. Solve for mass, we would say it's P over V, and of course, to solve for velocity, it's P over M. If the entire course is this easy and straightforward, we are laughing. Okay? I don't anticipate getting any kind of crazy difficult questions on your diploma exam with just straight momentum. Usually the more complicated questions come from putting momentum along with impulse or conservation momentum. Now, remember that little things, right? Remember that momentum is a vector. It has a direction associated with it. We can remember that if we do happen to forget it by taking a look at our data sheet and noticing that there's a little half arrow over top of the momentum sign, as there is with velocity as well. Velocity is a vector. Mass is a scalar. We remember that because there's no half arrow on top of the mass here. It has a direction associated with it. If the velocity is to the right, then the momentum is to the right. If the velocity is south, then the momentum is south. Finally, I added one more little thing in here. It says momentum after acceleration. Generally, we're not dealing with a problem like that, but every once in a while it does rear its head. When we're looking for momentum after an acceleration, it might be a problem like, you drop a ball from a height of 10 meters. What's the momentum of the ball as it strikes the ground? Or a car accelerates from rest for 28 meters. What's its momentum after that acceleration phase? It makes the question a little bit more tricky, but in the end, all we got to do there is still use P is equal to m times v, but find the velocity some other way. Like maybe vf squared is equal to vi squared plus 2ad. Maybe a is equal to delta v over delta t. Whatever equation happens to work to get the velocity. The bottom line is momentum is a quantity that exists at a single moment in time. What's the momentum now, or what's the momentum now? What's the momentum at the beginning of the problem? What's the momentum at the end of the problem? Okay, this would tend to be a what's the momentum at the end of the problem. And if the object is accelerating, then we would have to find the velocity at the end of the problem in order to plug into that equation. Now, one final thing before we move on to impulse, which we'll spend more time on because it tends to appear on an exam a lot more often. We talked yesterday, I think it was, about the 10 physics principles. The first physics principle that's on your data sheet in the bottom left-hand corner is uniform motion. Uniform motion is when we have v is equal to delta d over delta t, right? Whenever we use that constant velocity equation. Okay? I doubt that you would get a question that asks you for the physics principles if it was just a straight momentum question. But if you do, it will either be, and I missed one here, it will either be uniform motion if we're dealing with a constant velocity, okay, if the object isn't changing velocity, which would be the majority of questions involving straight momentum, but it could be accelerated motion as well. It would be accelerated motion if it was one of these situations down here, where you're looking for the momentum after it speeds up to a certain rate. Again, I don't think that you're going to see those two physics principles or any questions involving physics principles where it's just a straight momentum question. But if you do, it's going to be either uniform motion or accelerated motion. It won't be both. Okay, it won't be both, because you're not going to be going at a constant velocity and accelerating at the same time. We talked about impulse, and you can see right away the physics principles, really the only physics principle that you'll be dealing with when we talk about the concept of impulse might be accelerated motion. Why? Because what is impulse? It's the change in momentum. If momentum is changing, then it must be accelerating. It doesn't mean it's speeding up, could be slowing down, but the velocity is changing, it's accelerating, therefore it's giving us a change in momentum and impulse. I'm just going to say for the definition right here, delta P, right? You guys remember that delta P is change in momentum. And of course, the units would be exactly the same thing as we have for momentum. It would be kilograms meters per second, or it would be Newton times seconds. Now, we derived an equation for this. We're not going to derive it again, because in the end, it's on your data sheet. It says F times delta T is equal to M times delta V. What we usually do is tack on a little delta P in front of it, just to remind us that that equation, that two-part equation, or now that three-part equation, if I'm saying delta P is equal to Ft equals M times delta V, that whole thing is equal to the impulse. F times T is a change in momentum, M times delta V is a change in momentum. I'm going to circle something in red here that is meant to draw attention to a really, really common mistake that people make. The equation is not M times V. It's M times delta V. If you guys remember on the written response test that you did for momentum, many of you, lots of you, calculated the force of impact between those two cars. Do you guys remember that question? Two cars collided. You had to do a whole bunch of stuff, including finding the force of impact on car one and the force of impact on car two. If you guys remember that, lots of you calculated the force of impact using impulse. You had the right idea, but you set F times delta T equals M times V, not M times delta V. You've got to make sure that you're using the change in velocity. The other thing that I want you to be careful of here, when you're solving for impulse, if there happens to be 2 or 3 or 4 objects, you're always using one of those objects. Don't get mixed up and say, oh, look, I have the initial velocity of the blue car and I have the final velocity of the red car. It doesn't matter. Those can't go together when you're solving an impulse problem. You've got to have the initial and final velocity of the blue car or of the red car, but not of, you can't mix and match initial and final velocity for two different vehicles. Now, of course, we got to be able to rearrange this. But this is pretty straightforward algebra, right? Nothing complicated about this. You want to solve for F. Usually it's going to end up being M times delta V over delta T, although sometimes it might be delta P over delta T, depending upon which two parts of the equation you're using. The other thing that you're often going to have to rearrange to solve for would be delta V. And of course, delta V is going to be F times delta T, or we could just say delta P over the mass. All right? I'd like to take a look right now at the first of 15 multiple choice / numeric response questions that we want to do today. I'm going to refer you to question number 2. It's on the second page of the booklet that I handed out to you. And I'm going to give you a couple minutes to look at that question, numeric response number 2, see if you can solve it, and then we're going to take a look at it. One thing that I'll caution you about as you look into this question, pay attention to things like delta V as opposed to V, right? Pay attention to things like one object, not two objects. And another thing, I should have mentioned this before, pay attention to vector nature. What do we mean by that? The direction. Okay, if we got something going to the right and then something going to the left, make sure you pay attention to the fact that one's going to be a positive, one's going to be a negative. All right, we'll set you free on those for a couple minutes here, and then we'll take a look at it. All right, most people are finished here. We're going to use impulse to solve this problem, right? Clearly, that's what we've been talking about for the past 10 minutes or so here, guys. But why? If this is a question on a test and your teacher hasn't been standing up at the front of the exam room talking about impulse for the last 5 to 10 minutes, how would you know that this is an impulse question? What leads us to use impulse to solve this question? There's 2 words in there that tell me right away that this is almost certainly going to be an impulse question. Matt, do you think you know what they are? Is your hand going up there? All right, we got a change in momentum here, sure. The speed is changing. We're dealing with a mass. Okay, if that's the case, then there is going to be a change in momentum. Although that's often going to be the case, we're still not necessarily going to use impulse to solve the problem, even when there is an impulse. Depends on sometimes what we have given to us. 2 words here. Yep. It's a force and a time. When we see a force and a time, whether we have both of them or we have one of them and we want to solve for the other one, doesn't really matter. That's when we're going to use impulse. So I'm going to say F and T, we're going to use impulse to solve that problem. Or at least we're going to try to use impulse to solve that problem. Okay, worst case scenario, we try impulse, it doesn't work for me. It's not going to lead me astray because we know if there's a force and a time that there is an impulse, whether it leads us to the answer or not. All right, so what do we know about impulse? We know that delta P is equal to F times delta T, and it's equal to M times delta V. Looks like by our givens, it's the last 2 parts of the equation that I want to use, and I'm going to rearrange that to solve for F, get M times delta V over delta T. Notice what I wrote down there, M times delta V, not V, but delta V over delta T. We got a mass here. It's 5.7 times 10 to the minus 2. And we got to make sure here that when we put in delta V, we take into account not only the fact that there is 2 velocities here, an initial and a final, and there always has to be in one of these questions, even if one of them is 0, even if it starts at rest, VI is 0, there's still 2 velocities. We also have to pay attention to direction here as well. And one of the things that I probably should have done when I read through this question is to circle the north and the south to remind me when I plug my numbers in that I'm not going to forget to put one of them as positive, one of them as negative. The final velocity is 32 meters per second, so it's going to be VF minus VI, 32 minus negative 35. Another common mistake. Okay, first of all, forgetting to put the 35 in there to begin with. Second of all, forgetting to put the negative 35, making it 32 minus negative 35. Divide that by 4 times 10 to the minus 3. And when I do that math, I end up getting 9.55 times 10 to the 2. Anybody else get that? We'd express our answer A, B, C, D as 9.552. How many people got that? Good. You know what? That's 2% on your diploma exam right there. All you need is another 88%, and you've done fantastic on your diploma exam. All right. Let's go back to Physics 30 and 16 pages for a second. Again, we kind of addressed this in the question already, the vector nature of it, the direction nature of it. Okay, there is a direction associated with impulse. There is a direction associated with momentum. There is a direction associated with the velocity. In the end, if you have a positive velocity, negative velocity, right, left, north, south. If you have a positive impulse, that's going to mean a gain in momentum. If you have a negative impulse, that's going to mean a loss in momentum. Now, you can also think of it in a different way. A positive momentum, or positive impulse, I should say, a positive impulse means a gain in momentum, but it can also mean an impulse to the right, or an impulse to the north, or an impulse in the positive direction. A negative impulse means a loss in momentum, but we can also think of it as a momentum to the left, or a momentum to the south, or a momentum down, sorry, an impulse, I should say, an impulse to the south, an impulse to the left, an impulse downwards, and so on. So really, these mean the same thing. When you gain momentum, it means it's in the positive direction. When you lose momentum, it means the impulse is in the negative direction. And this is redundant. I should cross that off because I already put that, I guess, the equation and being able to rearrange the equation. Let's go back to this. Predetermined impulse versus non-predetermined impulse. This is the whole qualitative nature of impulse. Remember we talked about, these are my words, right? Predetermined, non-predetermined impulse. But in the end, what they mean is that in any situation, we either know what the impulse is going to be, or we don't know what the impulse is going to be. When I'm driving down the highway in my car, I know I'm going to stop eventually. I know what my impulse is going to be. I know what the mass of my car is. I know what the velocity of my car is. Therefore, I could calculate the momentum of my car. And I know at some point, my car is not going to be moving. My momentum of my car is going to be zero. So the impulse would be zero minus whatever the momentum of the car is right now. It doesn't matter how the car comes to a stop. The impulse will be exactly the same. So typically, we're talking about a predetermined impulse when you're stopping an object. When the car is coming to a stop, whether it hits the wall or whether it comes to a gradual stop at a stop sign. When the baseball comes to a stop, whether it stops because it hits your glove or whether it stops because it's just moving through the air, ends up hitting the ground, rolling for a while, and eventually coming to a stop. Or whether it hits your bare hand. Okay, the baseball is coming to a stop. We know what the impulse of the car is. We know what the impulse of the baseball is going to be, no matter how it comes to a stop. The other situation is the non-predetermined impulse. This is when we don't know what the impulse is going to be. Situation there is usually when we're starting an object. The golf ball sitting on the tee. I know its momentum is zero right now, but after I hit that golf ball, I don't know what its momentum is going to be. The baseball that's in my hand. I know its momentum right now, but I don't know what it's going to be after I throw it. Its impulse isn't predetermined. The car that's sitting at the stop sign. I know what its momentum is right now, but I don't know what it's going to be 2 minutes from now. I know what it's going to be. I know what the impulse is when the car is stopping, but I don't know what the impulse is going to be when the car is starting. That's a non-predetermined impulse. When an object is stopping, the impulse doesn't change. The momentum does, but the impulse doesn't change. The impulse is going to be the same no matter how it comes to a stop. So if the impulse isn't going up or down, then generally what we're going to try to do is increase the time that it takes to stop the object, which is going to have what effect on force? Smaller. That's your impact cushioning thing, right? That's the airbag in the car. Your head hits the airbag. Your head's going to have the same impulse whether it hits the airbag or the steering wheel or the pavement in front of your car. Your head's going to have the same impulse. But the airbag spreads the impulse out over a longer period of time. It takes longer to stop, which decreases the force. When you catch a baseball, you catch a baseball like this and kind of cradle it, as opposed to sticking your hand out rigid like this and not bending your elbow, right? You cradle it like this to increase the time that it takes to stop, to decrease the force. Spread the impulse over a longer period of time, increase time, decrease force. On the other hand, when you're starting an object, it's getting a little bit of a little cluttered here, but try to stay with me here. When you're starting an object, the impulse is not predetermined. When you're starting an object, increasing the force can increase the impulse. Force and time don't affect each other when it's not a predetermined impulse. Force and time both affect impulse when you're starting something, when it's not a predetermined impulse. So increasing the force increases the impulse. Hit the golf ball harder, you give it more momentum. The other effect is time. increase the time of contact, you don't decrease the force this time, rather you increase the impulse. So hit the ball harder, you give it more momentum. Hit the ball for a longer period of time, you give it more momentum. You understand the difference here? How force and time are related to each other in this one? Increase the time, decrease the force. By the way, you could go the other way, right? Occasionally, you might want to increase the force. If that's the case, you'd want to decrease the time. Okay. Bottom line is time affects force, though, not impulse. But in this one, when you're starting the object, time doesn't affect force. Time affects impulse. And force also affects impulse linearly. All right, let's take a look at another question. This is multiple choice number 3 on the booklet that I gave you earlier today. All right, let's have a look at this one now. It says airbags are a common safety feature installed in vehicles. When a vehicle suddenly stops, the airbag inflates. What's the purpose of that airbag? We know this, right? It cushions an impact. If any question you see involves cushioning an impact, we know what the answer is already. Whether we're talking about the airbag or whether we're talking about the baseball glove, or we're talking about the hockey pad, goalie pads, or whether you're talking about why you bend your knees when you jump off of the desk. In the end, what it is the impulse, which is predetermined. We want to spread that over a longer period of time, reduce the force. Let's read what it says, though. The force on the driver is less, the impulse on the driver is greater, the stopping time of the driver is longer. Which of the statements numbered above compares what happens in an automobile collision in which an airbag inflates with one in which the airbag does not inflate? Okay, so the airbag inflates. What does that do? Does that change the force on the driver? Sure it does. That's the purpose of the airbag, right? What does it do? It decreases the force on the driver. The impulse stays the same. Time goes up, force goes down. Time goes up, right? Stopping time of the driver is longer. Yes. Is the impulse greater? No. The impulse is the same. No matter how your head comes to a stop, the impulse is the same. So the answer is going to be options 1 or statements 1 and 3 here. I'm going to ask you to take a look at one more multiple choice question as well before we move on to our next little thing here. This is number 1, please, on the first page. All right, this question involves 2 collisions of pucks on an air table. It says in the first one, a stationary puck, puck 1, is struck by a second puck, puck 2. The mass of puck 2 is twice that of puck 1. So masses are different. It's a collision between 2 pucks where the masses are different. There is no friction, so we don't need to worry about that. Basically, hey, what are they telling us when there is no friction in this? We have an, what's the word I'm looking for? We have an blank system. We have an isolated system. There's no external forces acting. Okay, that really comes up later on when we talk about conservation of momentum. Okay, but it kind of appears a little bit here in this question. It's not really a big deal, but we can at least talk about that just a little bit here. We have an isolated system. There's no external forces, so we don't need to worry about anything like that here. Okay, a collision between 2 pucks. One puck is heavier than the other. Next one, we have a collision between 2 pucks head on. This time, the pucks have the same mass. They bounce back in the direction opposite to the original direction. Once again, we have an isolated system. There are no external forces. All right, what's the question here? It says, for collision 1, the magnitude of the impulse of the puck on puck 1 on puck 2 is blank to the magnitude of the impulse of puck 2 on puck 1. What's the answer there? Is it equal to or is it less than because of the difference in masses? Who says it's equal? Who says the magnitude of the impulse is less? The magnitude of the impulse is equal. Okay, it is equal. And the reason it's equal is because ultimately, if object A applies a force on object B will apply an equal and opposite force on object A. Right? Newton's third law, which is really just a statement of impulse, really, when it comes down to it. Okay, here's what happens. Puck number 1 loses a certain amount of momentum or gains a certain amount of momentum. Let's say it loses a certain amount of momentum. Where does it go? If it loses 10 units of momentum, where does that 10 units of momentum go? To the other guy, to the other puck. So if one of them loses 10, the other's got to gain 10. It doesn't matter that they have different masses or anything of the sort. Okay. In the end, if momentum is going to stay the same, then one gains momentum, the other's got to lose the exact same amount of momentum. Opposite signs, but same magnitude. What about collision 2? For collision 2, the magnitude of the impulse of puck 1 on puck 2 is equal to. Again, for the exact same reason. It doesn't matter that the masses are the same here. Okay, in the end, if one guy gains 10, the other guy's got to lose 10. Otherwise, momentum has disappeared somewhere. That can't happen. This will always be the answer to a question like this. If you've got a collision between two objects and one of them gains 5 units of momentum, the other must always lose 5 units of momentum. Even if one mass is 50 times the mass of the other one, the magnitude of the impulse will always, always be the same. Okay, let's take a look at another little aspect of impulse here, which is these force time graphs. I'm going to start that off by asking you those 3 words that I asked you way back in February when we did this for the first time. When you see a force versus time graph, and it looks something like this, you should always think 3 words. Kind of giving it away there because area equals impulse. Yeah, area equals impulse. I don't care if you're asked to find the impulse or you're asked to find something else. It doesn't matter. If you see a force versus time graph, you're thinking area equals impulse. Okay, it doesn't matter if it's shaped like this, if it's shaped like this, if it's got some kind of crazy shape, it doesn't matter. You want to think area is equal to impulse. Now, I've made a note here about units on axes. You got to be really careful with this, okay? You think the area should be easy, right? If it's a rectangle, then it's base times height. If it's triangle, it's 1/2 base times height. Okay? Generally pretty easy shapes, pretty easy equations. But what we often miss is the fact that the time might be in milliseconds or whatever. Or it might say times 10 to the minus 3 seconds. And the force may be in kilonewtons or millinewtons for that matter. Or it might say times 10 to the 2 newtons or whatever the case may be. Make sure you pay really close attention to the axes on the units. If it's in kilonewtons and milliseconds, then convert it when you're finding the area to newtons and seconds. Okay, if your area is 1/2 of 200 milliseconds times 30 kilonewtons, then what I want you to do is change that. Make it 1/2 of 0.200 seconds times 30,000 newtons. Make sure you're in standard units when you're calculating that area. Area equals impulse, make sure you're in standard units. Once you find the area, well, you've got the impulse. And then sometimes what you've got to do after you've found the impulse is find something else, like the change in velocity or the mass. And what you're always going to do there is set this equation, area equals impulse, also equal to m times delta v. Do not set it equal to this. Do not set it equal to f times delta t. Even though that's a valid equation, do not set it equal to m times delta v in this context. Here's why. The force here in this graph is almost always going to be changing. What value of f would we use if we wanted to use that equation in conjunction with it? Technically, it's valid, but you'd have to use the average force. And usually the average force is pretty hard to find on this graph. So just don't even bother going there. Area is equal to impulse, and that's equal to m times delta v. So if you've got the impulse by the area, given the mass, you could find delta v. Or, the other way around, given delta v, you could find the mass. So there's 3 variables in here really that you have to be able to find. Impulse, get the area. Mass, you take the area divided by delta v. Delta v, take the area divided by mass. One final thing before we do an example here, make sure you pay attention to what's above and below the x-axis. If you got a graph that looks like this, then this area, all 3 sections of it, will be positive. This area below the x-axis will be negative. And what we have to do to find the total impulse there is add them together. Plus 100 plus negative 50, or whatever the case may be. Get the impulse, that's what you're looking for, great. If you want to find mass or change in velocity, do your thing. Just make sure you've got the right value for impulse based on whether it's above the x-axis or below the x-axis. Let's take a look at another multiple choice / numeric response question. Now this one's going to be question number 4 on the 3rd page of your booklet. Time to take a look at it here. This question says, in a car safety test, we got a 1,200 kilogram car directed towards a solid wall. It collides with the wall, it comes to a rest, and then we got a force versus time graph here. What's the first thing you think of when you see this graph, force versus time graph? 3 words. Area equals impulse. Area equals impulse. Should be those 3 words every single time. We haven't even read the question yet, right? We just know the context of it. We know the information that we're given. We're thinking area equals impulse regardless of what we're asked to find. Okay, something that I noticed here though, almost missed it when I was doing my answer key. Got to be always aware of this, always alert for this. What is it that I'm talking about? Why did I pick up the red pen? Yep. We got kilonewtons on the y-axis, right? We got to be in newtons. And yeah, kilonewton is 10 to the 3 newtons. So it's a nice easy conversion. If we have 20 kilonewtons, we have 20 times 10 to the 3 newtons. Is there anything else I should circle in red here? We have seconds on the x-axis, but it does say times 10 to the negative 1 seconds. So it's easy when you're doing the base here from 3 to 8, just to say the base is 5. It's not really 5. It's 5 times 10 to the minus 1 seconds. So let's be careful of both of those things. We can find the area of this easily, but we have to pay attention to those units as well. All right, what does the question actually say? What's the magnitude of the impulse experienced by the car? All right, good. And what's the initial speed of the car? All right, we got to find 2 things. Okay, no worries. Okay, let's get the impulse here first by finding the area. The area is equal to delta P, which is equal to, because it's a triangle, 1/2 of base times height. The base here goes from 3 to 8, and I'm not going to forget that it's 5 times 10 to the minus 1 seconds, because I circled that 10 to the minus 1 seconds on the x-axis. The height of it, it goes from 0 to minus 70. So I'm going to say the height of it is minus 70 times 10 to the 3 newtons, or we could say minus 70,000 newtons. When we do the math, the area works out to be negative 17,500. Is that right? Okay, negative 17,500. That's the impulse here. Okay, that's the first thing that I'm looking for. Now I'm looking for the change in the initial speed of the car. It says comes to a stop, so the final velocity is 0. Now what I'm going to do is set delta P equal to m times delta V and solve for delta V. Delta V works here because although I'm technically finding initial velocity, since the final velocity is 0, the change in velocity will be the same magnitude as the initial velocity. So we're going to say it's negative 17,500 over the mass here, which is 1,200 kilograms. We do that math. Change in velocity works out to be negative 14.5833 meters per second. So if the final is 0 and it changed by negative 14.5, then the initial must have been positive 14.5. What do we got here? Impulse is 1.75 or 1.8 times 10 to the 4 newtons. And the change in velocity is negative 14.58 or negative 15, meaning the initial velocity must have been positive 15. How many people get A for that? Good. Anybody miss the change in units there, the kilonewtons or the 10 to the minus 1 seconds? Okay, one more that I'm going to get you to do before we move on to our next topic, actually. Question number 5. It's on the next page. Who's got an answer to this question now? Who thinks they have an answer to this question? Nobody wants to volunteer? All right, we got a couple votes for A, we got a couple votes for C here. Let's take a look at the question. It says, Plutonium-239 recovered from dismantled atomic weapons undergoes alpha decay and beta decay at the same time. Sensors on the outside of the containers used to store it can indicate how much radioactive material is contained by monitoring the gamma rays emitted by the material. It says a particular container holds this much waste. It's got a half-life, and it talks about the energy of the gamma ray and the speed of the alpha particle, so on. The question says, which of the following diagrams shows the orientation of the momentums of the alpha particle and the gamma photon and must result in the maximum impulse of the plutonium-239 nucleus? Listen, when you see this question, you're not looking at numbers. This has nothing to do with the numbers that are given to you. You got to look bigger picture here. You've got plutonium-239. Okay, here's the big plutonium-239. It decays into something else, okay, some other slightly smaller nuclei, an alpha particle, and a gamma ray. Right now, the momentum of this plutonium-239 is 0. If we want to maximize the impulse, and that's what the question says, right? To maximize the impulse, then we need to give it more momentum. It has 0 momentum. We need to give it lots of momentum. How are we going to give it lots of momentum? Maximize the amount of momentum we give it. Well, let's take a look at B for a second here. If it decays and the alpha particle goes this way with, let's say the value of this is 10. If it goes this way with 10 units of momentum, and the gamma ray goes this way with 10 units of momentum, these two cancel each other out. What's going to happen to the remaining daughter nucleus? It's going to stay where it is. Look, the momentum was 0 beforehand. If they're going in opposite directions afterwards, the momentum has got to be 0 afterwards as well. So B can't be the answer. Let's take a look at C now. That's the one that Carrie suggested there. Well, if the alpha particle goes this way with, let's say, 10 units of momentum, this looks like it's a little bit bigger, maybe 12 units of momentum, then the daughter nucleus is going to go this way. With how much? Well, we could use the Pythagorean theorem to find out how much momentum of the daughter nucleus was. Right here, well, we'd have to do components. But we know that the daughter nucleus would go back this way with a certain amount of momentum. Okay, in the end, this is the one that we care about here, because if the momentum of the alpha particle is 10 units to the right and the gamma ray is 10 units to the right, then the daughter nucleus must end up having 20 units in the opposite direction. You can't get, if this is 10 and 12, or 10, I think this is supposed to be the same length actually, 10 and 10, you can't get 20 out of this guy by having two 10s at right angles to each other. You can't get 20 out of this guy by getting two 10s at funny angles here. Okay? You get the x component of each of them combining back here, which is less than 10. Does that make sense? Understand why A is the answer there? All right, let's take a look at our next topic now, which is topic number 15, conservation of momentum in one dimension as opposed to conservation of momentum in two dimensions. You can see that if you get a problem involving this, it's pretty easy physics principle to identify if you happen to have one of those questions involving physics principles. It's conservation of momentum, right? Okay. There's nothing else really that can apply here. Now, that's not to suggest that you can't get a question with momentum involved like this, but also something else leading up to that. Maybe you've got conservation of energy where something is speeding up to a certain speed, and then there's a collision taking place where it's conservation of momentum. But if it's just a question like we're about to see, then we're dealing with one physics principle, principle number 4, conservation of momentum. All right, we talked a little bit about this one earlier, an isolated system. That's a system in which there's no external forces acting. No friction, no wind or anything like that. In the end, we can't always isolate a system from external forces by removing those forces. So what we often see is a question where we're asked for the velocity of an object immediately after or immediately before a collision. That means that, yeah, maybe there is friction, but since we're dealing with the velocity immediately before and immediately after, we haven't given friction a chance to really do anything yet. So we still consider that to be an isolated system, because although there are external forces, they don't come into play until the object just had a chance to move after the collision or explosion has taken place. All right. When do we use this? This whole idea of conservation of momentum, this whole idea that momentum stays the same when we have an isolated system. Well, we have a collision or we have an explosion. And by collision, we mean literally two things hitting each other. Okay, an explosion literally means one thing that breaks apart into two or more things. Explosion doesn't necessarily mean a bomb breaking up. It could mean something like a gun being fired. Bullet goes one way, the gun recoils the opposite way. Or maybe a balloon filled with air, okay? You got the balloon filled with air and you got the end of it held with your fingers and then you let it go. The air goes one way and the balloon goes the other way, right? Here's a good question. Not so much conservation of momentum, but takes us back to something that we did here earlier today. If I've got that balloon in my hand filled with air, and then I let it go, the air goes one way, the balloon goes the other way. If the balloon happens to gain 10 units of momentum to the north, then what's the momentum of the air that's going out the back of the balloon? If the balloon was in my hand, and now when I've let it go, the balloon's going forward with 10 units of momentum, then the air must be going backwards with 10 units of momentum, because the impulse experienced by the balloon must be the same as the impulse experienced by the air. Even if the air is lighter, balloon is heavier, or vice versa, it doesn't really matter. The impulse is always going to be the same. All right, back to this. Whenever we've got a collision or an explosion, we're going to do this whole conservation of momentum thing, which says PI equals PF. Count up your objects, put an MV term in for every object. Maybe it's M1 V1I plus M2 V2I plus, and so on and so on and so on, depending upon how many objects we have. Equal M1 V1F plus M2 V2F, and so on. If they stick together, then the masses combine, and we typically see it written like M1 V1I plus M2 V2I equals MVF, M being the combined mass. If they bounce apart, then we typically see it written as M1 V1F plus M2 V2F. Literally, just count the objects that you have before and after the collision and or explosion, and put an MV term in for each of them. Pay attention to positive versus negative in your calculations. Okay, that's important. That's so important. Again, take you back to that written response test that we had several weeks ago on momentum. We had the collision between the two vehicles, the car and the truck. One of them was going to the north, one of them was going to the south. And lots of you nailed that question. Lots of you got it correct. But lots of you didn't get it correct because lots of you failed to take into account that one of the objects was going to the south before the collision. So you forgot the negative. Okay, when you see that question, north, south, east, west, circle in red to remind yourself of signs. Okay, circle north, circle south to remind you that it's got to be opposite signs. Okay, units. What do we know about units with conservation of momentum? Typically, we're going to be using kilograms and meters per second for mass and velocity. But in a conservation of momentum problem, it doesn't actually matter as long as you're consistent. How come? How come? If I'm looking at this equation right here, how come I could use grams for mass if I wanted to? Even though kilograms are the standard units. Ali, you look like you're ready to give me an answer, but yeah, they cancel out, right? If they appear in every term, then they cancel out. Now, it's not necessarily the same mass in every term, but it's the same units in every term, so the units could cancel out. If in doubt, what should you do? If in doubt, you're not sure what units you should be using, what should you do? Go to the standard, right? Go to the standard units, kilograms in meters per second. Because you almost always have to do that. It's just the odd situation like conservation of momentum we can get away without doing it. All right. I'm going to give you a question to work on before I talk about what I mean by a progressive collision. We'll talk about that in just a couple of minutes. The one that I want you to work on now is going to be question number 6, please. Question number 6 on the same page as the question you just did. It's a skateboarder question. All right, a skateboarder who has a mass of 50 kilograms is running at a speed of 4.5 meters per second. Skateboarder jumps onto an initially stationary skateboard that has a mass of 4.2. What's the speed of the skateboarder and skateboard after this interaction takes place? This is like a collision, right? It's not literally a collision where two cars hit each other, but it's one object hitting another object or becoming one with the other object. So we're going to say it's a conservation of momentum problem. Pi is equal to Pf. We've got two objects before this collision takes place, so we're going to say m1 v1i plus m2 v2i. And then we have one object afterwards because the skateboarder and the skateboard become one object. So we're going to call it mvf. We plug in our numbers here. We don't have to worry about signs in this. Everything is in the same direction. Units are all standard units. So it's a rather straightforward example of one. 50 times 4.5 plus 0 equals the combined mass of 54.5 kilograms times VF. And we do the math on question number 6, and I think it works out to be A, 4.15. How many people get that? All right, good. What did I mean by that progressive collision? We don't see that very often. But we did see one of these on a unit test that we had. I think it was a test or a quiz or something that we had at one point. I'm going to give you that same question again in a few moments here. But essentially what I mean by this is a progressive collision is when there's a collision that takes place which goes into another collision. So let's say it's kind of like a domino effect, right? You're running, you're playing football, and you're running down the field, and you hit somebody. Okay, and you knock that person out of the way, and then that person hits somebody else. That's a progressive collision. Now, how do we deal with that? Well, we can deal with it as two separate collisions. We can say Pi equals Pf for the first collision, and then for the second collision, Pi equals Pf. But Pf for the first collision would be Pi for the second collision. Does that make sense? So basically what I'm saying is, let's not call it I and F because there's three different there's two different initials and finals here. Let's say P1 equals P2. So the initial momentum equals the final momentum. And then the momentum from this one becomes P3. So we'll say P2 equals P3 because the final momentum for the first collision becomes the initial momentum for the second collision, and then P3 equals P4. These are my two collisions. These are my two collisions here. Okay, here's the final momentum for the first collision. Here's the initial momentum for the second collision, but the final momentum for the first collision equals the initial momentum for the second collision, right? Okay. I collide with you. You bounce off with a momentum of 10. Okay, you hit somebody else. You hit them with a momentum of 10. Your final momentum in my collision is your initial momentum in the next collision. Take a look at what I just wrote down, though. If P1 equals P2, and P2 equals P3, and P3 equals P4, then how can we simplify this? P1 equals P4. So if you've got a progressive collision, which we're about to see in a second, you can go through the process of finding the initial and final momentum a couple of times, a couple of different problems, but you can simplify it by simply looking at the initial momentum before anything happens and the final momentum after everything happens. You don't have to look at each individual collision. You can, but it's twice as much work if you want to do that. Let's take a look at this question, please. That you have seen before, but you're not likely going to remember the answer for. Okay, let's have a look now. We got three cars here. Car 2 and car 3 are at rest before anything takes place. Car 1 is moving at 4 meters per second. Car 1 collides with car 2. Then car 1 and car 2 both combine and collide with and stick to car 3. So before all this is said and done, okay, car 1 is the only one moving. After all is said and done, car 1, car 2, and car 3 have all stuck together, and they're moving off as one object. Okay, you can treat this as two collisions if you want. Pi equals Pf for the first collision, and then Pi equals Pf for the second collision, or you can just look at it as Pi equals Pf for the entire thing. The initial momentum would be m1 v1i, because there is no momentum for the second object or the third object. Now, if the second or even the third object was moving before this collision took place, then we'd have to add a term for that. Even if there was all three objects moving, we would say m2v2 I plus m3 v3 I, whatever the case may be. They're not, so we can ignore those terms. Okay, but it's possible that down the road they could be moving before the collision. You have to include those if they are. Afterwards, they stick together. We're going to call it MVF, M being the total mass here. The mass of object number one is 1,500 kilograms. V1I is 4 meters per second. The total mass, I got 4,500, is that right? 4,500 kilograms times VF. We're going to solve for VF here. And when we do, it works out to be 1.33 meters per second. We'd express, this is kind of an odd one to express, 1.33. On our numerical response answer sheet, we'd put it as 1.33. Notice 3 significant digits, right? 3 digits, 1.33. Not scientific notation, nothing like that, just a number. All right, we're going to do another one here now. This is question number 9. But I'm going to do this one with you. This one talks about a lab, which basically we did. We pretty much did this exact lab in class, except we didn't use ticker tape or spark timer. We used our SparkView app along with our motion sensors in order to detect the motion. But in the end, we did the same thing essentially, where we took 2 carts, cart 1 and cart 2. Cart number 1 was initially at rest. V1I was 0 meters per second. Cart 1 was moving. We sent moving at a certain speed. This should have been V2I. V1I with a certain speed that we manipulated, that we changed through the experiment. Okay, they stuck together. We had this little plasticine. Okay, next year, based on some of your sources of error, when you did that lab, next year I'm going to stick some Velcro to both of these carts. They're going to stick together a little bit better. Regardless, they stick together. They go off as one object. We plot a graph of VF, the final velocity of both objects combined, versus the initial velocity of car number 1. Car number 2 doesn't have an initial velocity, so there's nothing to plot there. And this is the data that we get. Just a bunch of data points. Now, normally we draw a line of best fit for this, right? Most times we don't actually have to, on an exam, draw the line of best fit. For this one, we actually do have to, and you'll see why in just a second. Let's skip to the question, not question number 8, but question number 9, and see what they're asked to find. We'll see what we're asked to find. Based on a point on the line of best fit, cart 1 has a speed of 6 centimeters per second before the collision. Then the combined speed of the 2 carts after the collision would be A.B centimeters per second. Okay? Based on a point on the line of best fit. We don't have a line of best fit, so you're going to have to draw one. Okay? What you don't want to do is just go over to 6 seconds and then go over here and say, all right, at 6 seconds, we're at 2.4 centimeters per second. That's not a line on the line of best fit. Take a ruler, draw your line of best fit. We don't usually have to do this, but occasionally we do. Okay, a line of best fit might look something like this. Now, the good news is, if you're just reading a point off of the line of best fit, you're probably going to get this right if your line of best fit is even remotely close to being reasonable. Okay, if you draw it crazy, then you're going to get the wrong answer, but they'll accept a range of answers here, as long as it's consistent with a reasonable line of best fit. Okay, we wanted to find here the speed of the combined mass if the speed of cart number 1 was 6 meters per second, or 6 centimeters per second, I should say. So we go up, we go over, and it looks like we get about 2.5, 2.6. This would be 2.5, this would be 2.6, 2.55 or 2.6 centimeters per second. We didn't have to do anything crazy difficult there, right? No calculated work, no analysis of the graph really, other than up and over. We're going to fill in, by the way, the AB with 2 and 6. The combined speed of the 2 carts after the collision would be 2.6 centimeters per second. Now, based on the slope of the line of best fit, the combined mass would be what? This is where it gets trickier, right? But that's okay. We know how to deal with this. Based on the slope of the line of best fit, what's the combined mass? Let's figure out what the slope means. Y is equal to mx plus b. The y-axis is VF. M is the slope. The x-axis is V1I. Now, the y-intercept is pretty close to 0. Looks like it's close to 0. Don't know if it's exactly 0, but I think it's going to be close enough. We'll wait and see what the other equation looks like first before we decide for sure whether the y-intercept is going to be 0. What other equation from my data sheet or that I can derive might go with this? Don't necessarily go straight to your data sheet. Just think about what's going on. This is a collision between two carts. What do you usually do when you have a collision between two carts? Okay? Good. Pi equals Pf. So let's do that. Okay, let's try that. That seems to be the relevant equation here. Pi equals Pf. We're going to say M1 V1I plus 0, because the second cart is at rest, equals MVF, M being the total mass. Let's rearrange this to solve for VF. It becomes M1 over MT times V1I. This works. Right, Carrie? We said that we have to have an equation that has the same variables in it. Pi equals Pf has the same variables, VF and V1I. We cross off VF, we cross off V1I, and we're left with the slope is equal to M1 over MT. If we want to find the total mass, then all we're going to do is take the initial mass, the first mass, and divide it by the total. Divide it by the slope. The first mass is 1.54 kilograms. We don't know what the slope is. So let's do this together on our calculators, okay? Everybody pull out your calculator. And let's go through this process. We're going to say stat, edit. When you go there, it should probably be blank. If it's not, just go up to L1 and press clear. Now let's enter our data points. Now, you got to be careful here, okay? If you look at, make sure you get these data points correct, okay? I got the first data point to be 1.4 and 0.4. 1.4 and 0.4. What's going on here? There we go. Now I got my second data point here to be at 2.4, because each of the x-axis intervals is 0.2, and looks like 0.9. 2.4 and 0.9. My next one looks to be 3.2 and 1.15. That one's tricky. 1.15. Look at this. Okay, this is 1.1. This is 1.2. I'm halfway in between, so I'm 1.15. My next data point is 4.3, and I've got 1.75. My next data point is 5.4, and I've got 2.3 on my y-axis, 6 on my x-axis, and 2.4 on my y-axis, 6.4 on my x-axis, and the last one here is 3 on my y-axis. So there I've got, what is it, 1, 2, 3, 4, 5, 6, 7 data points here now. Remember, you hit stat, edit. Now it's going to be stat, calc. Option 4, linear regression. Keep hitting enter until you get a number here. My slope is 0.485. So I'm going to take the first mass that I got, which was 1.54, divide it by 0.485. When I do that, I get 3.2. So my total mass here, my combined mass, which is what they're looking for here, is 3.2. 2632 would be my answer. Yep. We're getting there. Now we're talking about two-dimensional collisions and or collisions in 2 dimensions, though. We got really 3 kind of interactions that we're going to see here. There's the T-bone collision, which looks like this. And then typically we have them going off as one object afterwards. We have what we call a glancing collision, which is something like this. Two objects hit each other, but not straight on, but kind of at the edge, and sends one way and sends one another way. And then, of course, we have the explosion, which is like, you know, we got one object that splits up into 3 or 4 pieces like this. Sometimes in a collision, they stick together. Sometimes they bounce apart. That's no different than a one-dimensional collision. If they stick together, it's M1V1I plus M2V2I equals MVF. If they bounce apart, it's M1V1F plus M2V2F. How do we do these questions, though? Right? How do we do the first one, the red one, the blue one, or the green one, the T-bone collision, the glancing collision, or the 2D explosion? Well, the good news is if you can do one, you can, for the most part, do any of the 3. We break them up into X and Y components. And for both the X and Y components, we say PI is equal to PF. In this case, it would be M1 V1I plus M2 V2I equals MVF because they stick together for both the X and the Y. In the second case, it would be M1 V1I plus M2 V2I equals, they bounce apart, M1 V1F plus M2 V2F. If we're talking about the third case over here, then it would be 0 initial momentum because it's an explosion, right? The object's at rest equals M1 V1F plus M2 V2F plus M3 V3F because we'd have 3 objects after the explosion takes place. Do the same thing for the Y component. Solve for, usually it's going to be VF for both the X and Y components. Get both of them, the X component and the Y component of VF. And then do the Pythagorean theorem. Simple as that. Sometimes, especially in these glancing collisions here, we got a funny angle. What do we do? What do we do if we have a funny angle? Matt, what do we do if we have a funny angle? Yeah, we don't like funny angles, right? So we get rid of the funny angles. Okay, if I have something like this that's at 25, let's make it 30 degrees because it's easier math. If I have something like this that's 10 at 30 degrees, then just take it off to the side over here and solve for an X and solve for a Y. The X component would be cosine 30 degrees is equal to X over 10, and the Y component would be sine because it's opposite. Sine 30 degrees is equal to Y over 10. Solve for X, solve for Y, and then whatever value you get for X goes into VF for object number 1. Okay? Don't worry too much about units here. Just be consistent. Okay, kilograms usually, and that's a standard unit. If you're confused, just go to kilograms, meters per second. But in the end, you know that you can use grams or kilometers per hour, whatever you want. Make sure that you resolve the components. If we got a funny angle, don't ever go with a funny angle. Okay, get rid of it. Get rid of the funny angle into an X and a Y components. Know how to deal with those. Remember to always, man, I'll tell you, like, you wouldn't think that this would be a problem, but it is. Remember to always break it into X's and Y's. It's too often people see a collision like this, and then they just have this brain freeze, this brain fart where they forget to break it into X and Y's, and they just say M1 V1I plus M2 V2I equals whatever. You can't do that. If it's a collision like this or any kind of two dimensions, anything like that you see above, you have to break it up into X and Y components. Pay attention to the positives and negatives. This is kind of repeat, right? Because we talked about most of this stuff with one-dimensional. The only thing that really separates this from the one-dimensional collisions that we've already done, really this, right? It's really the only thing that makes it different than these questions that we've already done earlier today. We'll talk about J and K in just a couple of minutes. What I'd like you to do right now is have a look at a couple of questions here. First of all, question number 10 in the booklet that I gave you. Just now. All right, the question says, after the explosion, we want to find the piece of speed, or the speed of piece C here. Look, don't just say PI equals PF for this, right? We just went through this. We just said that when you've got something like this, or a glancing collision, okay, like this, or you've got an explosion like this, okay, or a T-bone collision like this, you can't just do PI equals PF. It's got to be PI equals PF twice on the X and the Y axis here. So let's do that now. Let's break it up into X component and Y component. Let's say for both of them, PI equals PF. For both of them, the initial momentum is 0 because it's at rest, right? 0 is equal to M1 V1F plus M2 V2F plus M3 V3F. And for the Y component, same deal. 0 is equal to M1 V1F plus M2 V2F plus M3 V3F. Good so far? Plug in your numbers here. But be careful. Be careful you look at either X or Y at one time here. X components. We'd say object number 1 has 0 momentum. Even though it's moving on the Y axis. Object number 2 is 2 kilograms times 44.6. And object number 3 is 4 kilograms times V3F. We solve for V3F there, it works out to be negative 22.3 meters per second. And you do the same thing for the Y component, but this time there is a Y component. It's 3 times 39.2. Know what's initial, know what's final, and know what is X, and know what is Y. And don't mix those up. The Y component of the second one is 0 because it's all on the X-axis. Solve for V3F here, and V3F for the Y component works out to be negative 29.4. And we got to combine them. We got negative 22.3, negative 29.4. We're going to solve for V there. We don't need to solve for theta. Okay, but we could using the tan function. V is just going to be the Pythagorean theorem, and it's going to work out to be 36.9 meters per second. If all these masses were the same, what could we do to simplify this? If they were all 4 kilograms, we could cancel the mass. Would you have to cancel the mass? Of course not. But you could if you wanted to save yourself a little bit of time and effort. We go back to this now. And J within topic number 16 says problems given an unknown angle. A lot of times we've got a question where we have to solve for that angle, right? We're given the unknown angle this time, right? If we're given the unknown angle, then we don't have to treat it any differently. We can do it the way we just did. But notice when we just did it, we didn't pay any attention to that angle because oftentimes we don't have that angle. So I did it as if we don't have the angle so that you can do any question like this, whether you have the angle or not. But Matt, you're right. There is a shortcut here if you recognize that you have that angle. Let's get rid of all of this for the y component. And then let's say the x component is 22.3. The angle is 37.2. Okay, we can find this speed just by using the sine function now. Sine 37.2 degrees is equal to 22.3 over v. So you can save yourself some time if you're given that, quote, unknown angle. It's not really an unknown angle, right? But it's the angle that we're often trying to find. If we've got it, there's a shortcut, but you never have to take that shortcut. It's just a little bit of a time savings if you spot it. But you got to be careful. Sometimes people are looking for shortcuts, right? And you take 5 minutes looking for a shortcut that's going to save you 2. Well, you haven't really taken much of a shortcut then, right? If you spot it right away, great. If you don't, just do it the regular way. Oh, you're going to love this one. Look at this one. Let's do this one together, okay? Ozone in the upper atmosphere protects life by absorbing dangerous photons of ultraviolet electromagnetic radiation produced by the sun. When such a photon collides inelastically with a initially stationary ozone molecule, the molecule is broken apart into an oxygen molecule and an oxygen atom as shown below. Before the collision, after the collision. Listen, we're talking about photons here, we're talking about oxygen molecules, but when you look at this, I think it's pretty clear that this is a collision, right? And this is a conservation of momentum problem. We got to do x and y components because of that. But what do you got to do first? What's the first thing you got to do? I don't like funny angles. Get rid of the 74 degrees. Look. I don't care if it's photons or oxygen or atoms or molecules or ozone. I don't care any about that. Listen, I know what to do here. My velocity here was 220 meters per second. I can find the x and I can find the y by using some trigonometry, cosine and sine. And when I do that, I'm not going to show all that work here because I think you can do that. I end up getting 60.6402 for x, and I end up getting 211.4778 for the y component. Now I break it into my x's and y's. Now that I've dealt with that funny angle that I don't like, I do my x's and y's. Pi equals Pf. I'm going to say, look, I've got the momentum of the photon. If I had the wavelength, I could find the momentum by saying h over lambda. If I had the energy, I could find the momentum by saying E over C, using those equations in the top right-hand corner of your data sheet. But I've got the momentum here. The momentum of the photon is 9.3 times 10 to the negative 24 plus 0, because the ozone is at rest, plus the mass of the oxygen, which is, equals, I should say, the final momentum, the mass of the oxygen times, you guessed it, the x component of the final velocity of the oxygen, 60.6402, and then we add to that 2.66 times 10 to the minus 26 times Vf. So momentum of the photon plus the momentum of the ozone, momentum of the molecule plus the momentum of the atom. We solve for Vf there, it works out to be 228.5716. Now, Matt, if I had, we know the oxygen atom is going to go down here somewhere, right? If I had this angle given to me already, what could I do? Yeah, I probably end up using cosine because I found the x component. I've got the, I'm looking for the hypotenuse. Cosine theta is equal to x over 228 over the hypotenuse, right? But I don't have that unknown angle. In fact, I'm looking for it. So I've got to go through that process now of finding it. Y components, we're going to say 0 initial momentum on the y-axis, because everything's on x, right? Is equal to Here's the molecule, 5.31 times 10 to the minus 26 times 211.4778. This is the Y component of the final momentum of the molecule. Plus 2.66, this is the atom. Solve for VF. And we get negative 422.1606. Listen, this is an easy question now, right? Do the same thing as we always do now. Do the same thing as you did for the last question, same thing as you do for every other 2D question. 228 422.1606. We could find theta by the inverse tan function, and we can find V by using the Pythagorean theorem. I'm not going to go through that because I think you're okay. If you need me to go through it, I will, but otherwise I'll just give you the answers here. V is 480. And theta works out to be 61.6. Okay. We'd say that would be, if this is a north, south, east, west thing, then we'd say that would be 61.6 degrees south of east, because we went east. Then we went from the east, Gary. We went south from the east. South after the east or south from the east. Okay. Look at the angle here. It's measured not from the south, because this is south. It's not even touching south, right? It's measured from the east axis, but it's south from the east axis. It's below the east axis, so it's south of east. All right, let's take a look at our last thing here, which is elastic and inelastic collisions now. Just a couple quick little reminders. An elastic collision, remember, is a collision in which kinetic energy is conserved. Remember, if they stick together, it's always inelastic. If they stick together. If they bounce apart, could be elastic, could be inelastic. Don't know. When we see a question, we hope for them to stick together, because then we have a definitive answer without doing any calculations. If they stick together, it must be inelastic. If they bounce apart, it's probably still inelastic, but it could be elastic. Scalar nature, always positive, no angles, right? This is when, even in a question like this, we would not break it up into x and y components. Why? Because momentum is a vector, but kinetic energy is a scalar. So all you're going to do is say, whether it's a one-dimensional or two-dimensional, whether it's north and south or north and north, you're going to say EKI equals 1/2 m1 v1I squared plus however many objects you have. Get a number. Do the same thing for the final. And if those two numbers are the same, it's elastic. If EKI is bigger than EKF, it's inelastic. EKF won't be bigger than EKI. If it is, you've made a mistake. Units, joules, always want to use joules here. We've used electron volts a lot now since we've gone through atomic physics. Don't use electron volts here. Okay, use joules. And remember, again, just with the scalar nature, always positive, no components, okay? No funny angles, okay? This is the one time when you can say, listen, I don't like funny angles, but they're not really bothering me right now. Okay, if you're dealing with a scalar, funny angles don't matter. You can hate them all you want, but just to leave them alone when you're dealing with a scalar. And finally, before we do a quick example here, finally, in an elastic collision, kinetic energy is conserved, so is momentum. In an inelastic collision, kinetic energy is lost. Momentum is still conserved. Doesn't matter what kind of collision you have, momentum is conserved. First example I want to do with this goes back to question number 8. Goes back to this information on the graph that we already did. Question number 8 says, the collision of the two carts is classified as blank because blank. Man, I'm telling you, I'm really hoping these two things stick together because I don't want to calculate EKI and EKF. I'm not sure what VI and VF I'm going to use because there's 7 different data points for VI and VF. When you look back at the information, though, lo and behold, they do stick together. And because they stick together, we know that this is what kind of collision? Inelastic. We know it's inelastic. And why do we know? And what happens in an inelastic collision? Kinetic energy is not conserved. Is momentum conserved? Yes, it is. Momentum is conserved. Kinetic energy is not conserved because it's inelastic. The other one that I want to do is multiple choice number 12, which is going to be towards the back of your booklet, if I can find it here. It says, in a classroom demonstration, 2 identical low-friction dynamics carts are pushed toward each other such that they're traveling at the same speed when they collide. Okay, so 2 cars collide, 2 carts, same mass, same speed, collide. They come to a complete stop. Teacher challenges students to describe this collision. Some of the students' descriptions are provided below. Before the collision, the carts have the same momentum. Before the collision, they have the same kinetic energy. This is an example of an elastic collision. This is an example of an inelastic collision. Which ones are correct? Do they have the same momentum before the collision? Oh, this is a great question. Do they have the same momentum before the collision? They have the same mass. They have the same speed. Do they have the same momentum before the collision? Who says yes? Who says no? Why do you say no, Allie? Good. They have the same magnitude of momentum. They do not have the same momentum. Momentum is a vector. The momentum of one of them is whatever value to the right. The momentum of the other one is the same value to the left. Those are 2 different momentums. They do not have the same momentum. They have the same magnitude of momentum. But momentum is a vector. We have to pay attention to direction. Do they have the same kinetic energy? Yes or no? Who says they have the same kinetic energy? Who says they don't have the same kinetic energy? They do have the same kinetic energy. They have the same mass and they have the same speed. Momentum depends upon velocity. Kinetic energy depends upon speed. They do have the same kinetic energy. Elastic versus inelastic. Clearly, it can't be both. Is it elastic or is it inelastic? We don't know how fast they're going here, so I'm not sure how we're going to do a calculation. Elastic or inelastic? Who says elastic? 2 objects, same speed, same mass, hit each other, come to a stop. Who says elastic? Who says inelastic? Hugh, why do you say inelastic? Okay, if in doubt, go with inelastic. Because 9 times out of 10, or even more than that, it's going to be inelastic. Truly, only subatomic particles are elastic, right? Because they don't squish. Right? But you can get it. It's conceivable to get a collision that's really, really close to elastic. That could be technically classified as elastic. This is inelastic, though. It is inelastic. How come? What's the initial kinetic energy? I don't know, but something. What's the final kinetic energy? 0. Something does not equal 0. If object number 1 is 10, object number 2 is 10, combined it's 20. Not 0 because they're scalars, right? 10 and 10 is 20. Afterwards, the total kinetic energy is 0. We lost kinetic energy. Since we lost kinetic energy, it's inelastic. So what do we got? 2 and 4. There are 3 more questions that we're not going to do here right now. These are 3 questions that aren't in order. They don't really go at all in order with the topics that I've listed in that 16-page booklet. Just kind of, look, at the end of everything, after we've done going over the unit, maybe you want to take a look at 3 kind of random questions within one scenario. We're not going to do those right now. You want to take a look at those yourself and then come back and ask me how to do something if you had trouble. That's great. Okay, if you want to ask me Monday morning when you guys come in for your next extra help session, then you can do that as well. I will give you the answers, though, right now for questions 13, 14, and 15. Okay, number 13, the answer is C. Number 14, the answer is C. And number 15, the answer is B.